In this physics question, we're going over moments with forces at angles. We have some SUVAT 2, both a calculation as well as an explanation question. Okay, for the first part, figure 5 shows a simplified catapult used to hurl projectiles a long way. The counterweight is a wooden box full of stones attached to one end of the beam. The projectile, usually a large rock, is in a sling hanging vertically on the other end of the beam. The weight of the sling is negligible. The beam is held horizontal by a rope attached to the frame. The catapult is designed so that the weight of the beam and the weight of the empty box have no effect on the tension on the rope. So the weight of the empty box, the weight of the beam itself, they have no effect on the tension of the rope. We want to suggest how the pivot position achieves this. So that would be the case if the moment of those two forces cancelled out. So the weight of the box acts this way. The weight of the beam will therefore have to be on the other side of the pivot, over here somewhere, in order to cancel out the moment due to the weight of the box. The weight of the box would be a clockwise moment, following the line of action of the force and then going around the pivot. And the weight of the beam would be an anti-clockwise moment. Those two moments should be equal and opposite, about this pivot point. If so, they cancel out, and they will then have no effect on the tension in this rope. For 4.2, the stones in the counterweight have a total mass of 610 kilograms, and the projectile weighs 250 newtons. Calculate the tension in the rope. So let's draw a force diagram. Here is our beam. Here is the support. So remember that from the previous scenario, we know that the weight of the beam and the weight of the box, the moments due to those two forces cancel out. So for that reason, if we're considering a moments equation, we don't have to consider the weight of the beam and the weight of the box, as their effects will just cancel out. So we can just consider the weight of the mass that is attached on the right-hand side, which is 610 g. There is the weight of the projectile, which is 250. And finally, there is the tension force. All of these forces will have a moment about this pivot point. There is also a support force, but if we're taking moments about this point over here, we don't need to worry about that support force, as it will not have a turning effect. So just going back to our diagram, we're given a few distances and an angle. So we are given that this is 4 meters, this is 1.5 meters, and this angle here is 50 degrees. So let's put that on our diagram. Okay, so let's identify which moments are clockwise and which moments are anti-clockwise. The 610, if we start where the force acts and follow along the direction of the force around the pivot, that will give us a clockwise direction. So this force is a clockwise, or has a clockwise moment. And for these two forces, they will both go anti-clockwise about the pivot. Okay, so then we're setting clockwise moments equal to anti-clockwise moments. So it'll be 610g multiplied by the perpendicular distance is equal to 250 multiplied by its perpendicular distance. And finally, the tension force is at an angle. So what we have to do is we have to resolve the tension force perpendicular to the rod. So that will be this component here. That would just be t sine 50 using SOHCAHTOA. So the moment due to the tension force will be that component of perpendicular force, t sine 50, multiplied by the distance of 4. And now we can rearrange for t. T sine 50 times 4 is equal to 610g times 1.5 minus 250 times 4. So the right-hand side gives us 7967. Divide that by the 4 sine 50, and that will give us t, which is 2,600. (4.3) When the rope is cut, the counterweight rotates clockwise. When the beam is vertical, it is prevented from rotating further. The projectile is then released horizontally with a velocity of 18 meters per second, and it is released at a height of 7.5 meters above the ground. We are trying to work out the range of the catapult, which is basically the horizontal distance traveled. So this is a two-dimensional SUVAT question. Let's draw out a SUVAT table, consider our quantities both in the vertical and in the horizontal direction. So then, once we have our table filled out, we can then think of what equations to use. So we want to work out the range, which is the horizontal displacement. We have the horizontal velocity, 18. That doesn't change. There is no acceleration in the horizontal direction. The only acceleration is vertical. That's the downwards weight force that causes that acceleration, so 9.81 downwards. We also have a vertical displacement of 7.5. So I'll consider the downwards direction to be positive, in which case the displacement would be positive 7.5 and the acceleration would be positive 9.81. The initial vertical velocity will be 0 because it is launched horizontally, so there is no vertical velocity to begin with. So this is our table filled out now. We want to work out horizontal displacement. For these kinds of projectiles questions, in the horizontal direction, the only equation that we can use is speed is equal to distance over time, because there is no acceleration, and therefore that's the only equation that's available to us. So to use that, we have to know what the time is. To get time, we have to consider the vertical direction. So with the three quantities that we have here, we can use s is equal to ut plus half at squared to work out time. U is 0, so I'll write this as a half at squared. And then t is the same thing as 2s over a square rooted. Put the numbers in. 2 times 7.5 over 9.81. This gives us 1.237 seconds. And then we can use in the horizontal direction, we can do distance traveled is speed multiplied by time. And this gives us, to 2 sig figs, 22 meters. 4.4. In another release, the sling is adjusted so that a projectile of the same mass is released just before the wooden beam is vertical. The projectile is not released horizontally, and we want to discuss the effect this change has on the range of the catapult. Okay, so let's go back to this diagram that we have down here. So what's happening is, the beam is not rotating all the way through 90 degrees. It will end up in a position looking like this, where here is the counterweight, the mass would be here somewhere, and it will be launched at an angle to the horizontal like this. So that would mean that now there is a vertical component of velocity. Before we just had a horizontal velocity, there was no vertical velocity to begin with. Now that we have a vertical component of velocity, which is this bit here, that will increase the time of flight. The larger the upwards velocity, the greater the time of flight. If we go back to this calculation that we did over here, we worked out the time of flight, and then we multiplied that time of flight by the horizontal speed, and that gave us the distance traveled, or the range. If the time of flight is longer, then that could increase the range. But if we go back to the diagram, the mass that we have down here is not going down all the way to the lowest position that it could do, in which case we're not losing the same amount of GPE as we would if the beam were to be vertical. If we're not losing the same GPE, then this mass is therefore not gaining the same kinetic energy in the end. If it's not gaining the same kinetic energy, its horizontal velocity at launch would be lower. So then going back to this equation, if the horizontal launch velocity is lower, then that will lower the range. So we have two opposing effects here. One effect will increase the time of flight, and the other would decrease the horizontal velocity. So we can't actually tell which effect would be greater, and therefore the overall effect on the range is unknown.